Mm-hmm.
You ready?
Mm-hmm.
Glasses or no glasses? Okay.
Thank you.
I took a few. I did the Mark special.
Thank you.
I'll close my door, okay?
Mm-hmm. Hello and welcome everyone. My name is Mark Gillette and I would like to welcome you to tonight's presentation that I will be putting on entitled NASA's James Webb Space Telescope. There are so many exciting things happening at NASA. Just to give you a quick example of what I'm talking about, last month NASA launched the Lucy mission, which is a mission to go and explore the Trojan meteors of the planet Jupiter. Just last week on Wednesday, SpaceX brought home a crew from the International Space Station, Crew 2, and 2 days later, on the 11th, SpaceX launched Crew 3 to the International Space Station. SpaceX did both of these for NASA. Just in a couple weeks, on November the 23rd, NASA will be launching the DART mission. DART stands for Double Asteroid Redirection Test. Basically, this mission is going to have a small satellite crash into a small meteor, which is part of a binary system, to see if they can slightly nudge it off of its current course. This mission is to explore what we can do in the event if a meteor is headed towards Earth. And of course we have the Artemis program, and the first launch of the Artemis program, entitled Artemis 1, is scheduled for February of 2022. So as I said, there are a lot of exciting things happening at NASA, but tonight the focus will be on NASA's newest space telescope, the James Webb. So thank you so much for joining me. For those who don't know me, my name is Mark Gillette, and I'm a NASA JPL Solar System Ambassador. The Solar System Ambassador program is a joint venture between NASA and JPL in California. I've been a Solar System Ambassador now for 3 years. Generally what I do is I go out into my local community, a resident of Central Florida, not far from Orlando, and I do presentations at local libraries and even at the local jail. But last year with COVID, I decided that I would start offering YouTube live events. So if you are interested in seeing some of the events that I have done over the last year and a half, please feel free to take a little time later to go to my YouTube channel and look at the Solar System Ambassador folder, and you will see quite a variety of topics that I've offered over the last year and a half. So I'd like to give you a brief idea of what we will be talking about over the next 55 minutes. So here's a brief agenda. I'm going to be talking about how the James Webb Space Telescope, often simply referred to as JWST or Webb, is a international collaboration among 3 major space agencies. I'm going to be talking about the launch site, provider, and rocket that will be used to launch Webb. I'm going to talk about the journey both to the launch pad and out into space. I will talk about the spacecraft itself. I will talk about how NASA communicates with JWST, and then I'm going to talk about some of the important science that will be coming out of Webb. At the end of tonight's presentation, I will have a Q&A period. So during the presentation, if you come up with any questions, feel free to put them in the chat box, and I'm going to save all of those to the very end of the presentation tonight. So again, I'd like to thank you so much for joining me. And so let's go ahead and get started. I have a short little video that I'd like to show you, and I think it does a great job of giving us a good overview of the James Webb Space Telescope.
The James Webb Space Telescope is the next premier space observatory. It will extend the discoveries of the Hubble Space Telescope and observe the birthplaces of planets, stars, and galaxies. It is named after James Webb, NASA's second administrator and champion of many NASA science missions. At 3 stories high and the size of a tennis court, this will be the largest telescope ever sent into space, and 100 times more powerful than Hubble. It is so big it has to fold to fit into the rocket only 5.5 meters wide, and unfolds segment by segment once in space. Webb's mirrors are coated with a super thin layer of gold that is about 1,000 atoms thick to optimize their reflectivity in the infrared. Webb will launch from French Guiana. It is launched near the equator, taking advantage of Earth's greater rotation speed there to boost launch performance. Webb will orbit the Sun 1 million miles from Earth at the second Sun-Earth Lagrange point. The telescope will observe infrared light with unprecedented sensitivity. It will see the first galaxies, born after the Big Bang, over 13.5 billion years ago. Webb's infrared cameras are so sensitive, they must block light from the Sun, Earth, and Moon. The 5-layer sun shield is like having sunblock of SPF 1 million. Webb is an international mission, with contributions from the European Space Agency and Canadian Space Agency. Scientists all over the world will be able to use Webb to explore further into space and back into time.
Okay, so that's a quick overview of NASA's James Webb Space Telescope. So let me go back to my PowerPoint presentation here, and we will go into a little bit more detail about James Webb. Alright, so as mentioned in the video, the James Webb Space Telescope is indeed an international collaboration among 3 major space agencies, including NASA here in the United States, Canada, and ESA, the European Space Agency. And if you see the little white dots here on the map, basically these are all locations that had something to do with either the design, engineering, or building of Webb. Here are some other general information about JWST. The launch date is currently scheduled for December the 18th, so a little more than a month from now. It should be noted that originally it was scheduled to be launched in 2007, so the James Webb Space Telescope is running a little behind. Construction started in the year 2002. The life expectancy of Webb is between 5 to 10 years. And we hope that what will happen, much like the Hubble Space Telescope, which Webb is currently being seen as the replacement for Hubble, will actually last much longer than its expected life expectancy. Due to the distance that James Webb will be sent from Earth, it will not be able to be serviced. Consider that the Hubble Space Telescope, launched back in 1990 using the Space Shuttle Discovery, it was launched in what we call low Earth orbit. So the Hubble Space Telescope is roughly about 340 to 350 miles above the Earth, orbiting the Earth about every 90 minutes. James Webb will actually be positioned roughly about 1 million miles from Earth. With that said, unfortunately, there's no way to service Webb, no way to repair it. Unlike Hubble, that actually did need to be serviced a few times because of focusing problems with the telescope's lens, and it was serviced using the space shuttle, where the space shuttle would launch, go up, meet up with Hubble, pull it into the payload bay, astronauts would do servicing missions and then release it. For the James Webb Space Telescope, that's not going to be an option because it's going to be so far away from Earth. So it has to be right the first time. The cost of the James Webb Space Telescope is roughly about 10 billion US dollars. So a lot of resources have been put into this incredible piece of machinery. The prime contractor for Webb was Northrop Grumman. NASA's Goddard Flight Space Center has managed the development of JWST. The Space Telescope Science Institute will operate Webb, which is located at Johns Hopkins University in Baltimore, Maryland. That's some general information about James Webb. Let's take a look at the journey to the launch site. And it has been a long time and a long journey. But JWST was packed into a 98-foot container and shipped from Long Beach, California, through the Panama Canal to French Guiana. And French Guiana, as you can see there on the top right-hand map, is in the northeast corner of South America. And so you might be asking, so most launches that occur for NASA in the United States leave from Kennedy Space Center or Cape Canaveral Space Force Station in Florida, or there are a couple other launch sites that NASA will use on the West Coast and also on the East Coast of the US. Why is it going down to South America? Well, as mentioned earlier, there are other space agencies that are contributing to Webb. And one of the things that ESA is doing, the European Space Agency, is providing the launch vehicle and the launch site. Okay, so that's why it's being shipped down, or that's why it was shipped down to French Guiana. It was a 16-day journey, which started on September the 26th in California, and it did eventually end up getting down to French Guiana on October the 12th. All right, so this was just roughly about a month ago that it actually arrived. The Guiana Space Center is being used to launch Webb. So in the background, you can see some of the launch facilities. This is an aerial view. And then you also see two maps. On the left-hand side, you see the port in which Webb arrived into. And on the right-hand side, you see the actual Space Center and the layout of the different launch facilities and buildings that are used to prepare vehicles and payloads for launch. This is the ship that was used to ship Webb from California down to French Guiana. And again, it did arrive down there on October the 12th, so roughly about a month ago. From my understanding, when the ship completed its travel through the Panama Canal, it was no longer trackable because there were concerns of, believe it or not, pirates coming and trying to hijack the ship. And so if anyone was trying to follow along, there are certain apps, for example, that you can download on your smartphone, and you can follow all of the ships all over the world and where they're going. Apparently, NASA decided, hey, we're not going to publicize where the ship is going and when it's going to arrive at our predetermined destination, so they tried to keep it a secret. So quite interesting. All right, so as I mentioned earlier, ESA, European Space Agency, is providing both the launch site and the launch vehicle. And so on the right-hand side of your screen, you see the launch vehicle that will be used to launch Webb. It's an Ariane 5 rocket, and it's been designated Flight VA256. The Ariane 5 rocket is one of the most dependable rockets ever built and used globally. There have been many, many successful launches of the Ariane 5, and that was one of the major considerations that NASA took into consideration when determining how they would best launch Webb into space. Okay? They did not want to take the chance and use some type of launch vehicle that has not been extensively used and tested, because as you can imagine, many things can go wrong with rocket launches, and you don't want to put something as expensive as Webb onto a rocket where there might be problems and it will not end well. The Guyana Space Center that I showed you earlier is roughly about 310 miles north of the equator, which is at a latitude of about 5 degrees. That's also important, the location of the launch facility, because the closer that you get to the equator, the less fuel that is needed to generally get some type of payload and rocket into space. And so that's why the European Space Agency chose French Guiana to build a launch facility in the first place. So Webb will be launched, as I said earlier, and will travel roughly about 1 million miles from the Earth to what's called the Lagrange Point 2. Lagrange points were named after the man who discovered them, and basically a Lagrange point is a balancing area between two objects. In this case, it would be between the Sun and the Earth. Lagrange points are good places to put things like Webb and satellites because they are generally pretty stable orbits, and they don't require a lot of fuel to keep the mission moving along and moving. So I'd like to show you just this quick little animation about the orbit, how the orbit will work once it's out to Lagrange Point 2. So let me go ahead and increase the size of this for you so you can see it better, and I will restart it. Alrighty, let it play through. Alright, now there you go. So as you can see right here, this is Webb, this is the Earth. They stay basically very close to one another. Alright, and so Webb will not be orbiting the Earth like the Hubble Space Telescope. Webb will be orbiting the Earth. Will be orbiting the Sun. Okay, just like the Earth does. It will be in lockstep with the Earth, so it will go around the Sun at exactly the same time. Okay. So Webb will be permanently positioned at the second Lagrange point. It will not be moved from that place once it ends up there. The gravitational forces of two large bodies are balanced when you are in a Lagrange point. All right. So now let's take a look at the journey to L2. The James Webb Space Telescope will travel to L2 over roughly 30 days. You might ask yourself, are there other reasons why James Webb is being sent so far away other than the stability of the orbit that it will be in? And in fact, there are other reasons, and one of the biggest reasons is that the James Webb Space Telescope will be using infrared technology and imaging. And heat doesn't play very well with infrared technology unless that's exactly what you want to seek. So the Earth, much like the Sun, of course, puts out a lot of heat. Even the Moon does. So in order to get away from the heat, James Webb will be put many, many miles away from the Earth. On the sun-shielded side, the temperature will be roughly 390 degrees below zero. All right, on the sun side of the James Webb Space Telescope, it will be roughly 260 degrees Fahrenheit. And I'm going to talk a little bit later about the sun side versus the shielded side of James Webb. So most of the post-launch assembly will be completed within 2 weeks of launch. And you might be asking, well, what does that mean, post-launch assembly? Is someone up there putting it together? Well, no one's up there putting it together. But as mentioned in the video earlier, the James Webb Space Telescope is so large that it would not fit into the payload section of the rocket being used to launch it. So engineers had to design it to, in essence, fold up. And once launched into space, it has to unfold. And so here are some of the major steps that will occur during that unfolding process. So here's Earth. One of the very first things that will happen within just a few hours of launch will be the solar array deployment. The James Webb will be using 5 solar panels which collectively make up the solar array to power it. And the missions operators need to get that open as soon as possible so that they are powering the satellite as it moves out away from Earth. The second thing that will happen is an antenna, communications antenna will deploy from James Webb. That way NASA will be able to communicate with James Webb. Then we have the sun shield deployment, and here at the bottom, okay, this is the main instrument with the mirror, but right below it, that's the sun shield. And so the sun shield will have to open up and will have to start providing immediate protection from the heat of both the sun and the Earth. Okay? And then we will have what's called secondary mirror deployment. And this right here, this is the secondary mirror. And then the primary mirror will be deployed. And the big gold section right here is the primary mirror. Okay? So again, most of this will occur roughly within about the first 2 weeks of launch. But it still will take roughly about 2 weeks to get it to the L2 point. So it's roughly about a 30-day journey from Earth to the Lagrange second point. All right, so this is a little bit more in-depth view of that unfolding sequence that I was mentioning. So after launch, it will be in its launch configuration, all folded up. And then we have this is showing the sun shield that will be deploying. And you can see it just kind of opens up on both sides, but then it has to evenly spread out. And the sun shield is roughly the size of a tennis court. It's made up of 5 super thin layers, and each layer provides more and more thermal protection from the operations of the telescope itself. And so you can see as we come around over here, this is the secondary mirror that I was mentioning, and then the primary mirror. See how this is folded in? And so once it's open, it's totally open, it looks like that. Okay, so the interesting part of this is that all of this has to go right, because as I mentioned earlier, once Webb is launched, there's no way to go and capture it, catch up with it, and to fix it if anything goes wrong. Unfortunately, there are hundreds of things that could go wrong that could cause serious problems with for the success of this space telescope. For example, the sun shield. If anything happens, if anything gets caught as the sun shield is opening up, that could end the mission. If one of these two side panels on the primary mirror, if they don't open up and lock into place, that could end the mission. If the secondary mirror does not open properly, and I'm pointing to the secondary mirror here, again, that could end the mission. So there are many redundant systems that have been built into the James Webb Space Telescope, so that if one motor doesn't work to open up the sun shield, there's a secondary or redundant motor that hopefully will then take care of the job. There are, I believe, 8 or more motors that will help to open up the sun shield. There are hundreds of lock mechanisms that are keeping James Webb all in a locked configuration. They must all unlock properly and at the right time. And also there are redundant systems to help in the event if one of them for some reason gets stuck. So lots of issues, lots of potential issues. And so hopefully all will go well. So as I mentioned earlier, there are two sides. There's the observing side, which contains the mirrors, the primary mirror and the secondary mirror. And then on the opposite side, you see the bottom of the sun shield. And so the mirrors need to be kept extremely cold. And the way the engineers came up with accomplishing that task is by using these very thin 5 layers of material that will prevent heat from the earth and the sun penetrating through and kind of messing up the operations of the mirrors. Okay. There are several science instruments on board James Webb. There are some cameras. There's like the near-infrared camera. There's the mid-infrared instrument, fine guidance sensor, near-infrared imager, and slitless spectrograph, and the near-infrared spectrograph. So these are the main instruments that will be used to conduct all of the science that will be used on Webb. And so the way that it works is this. The light will be coming in. The light will hit one of the 18 hexagon-shaped mirrors that are all aligned to create one big mirror. That light will then bounce off of here up to the secondary mirror, all in this point right here. All the light from here will be directed here, and then that light will then turn around and go into here, which behind what you see here is what's called the tertiary mirror. Okay, so there are kind of 3 mirrors. The big primary one, the secondary one, and the tertiary one. So you're taking a lot of light, you're condensing it down to here, and you're taking this and condensing it down into there. And so behind there where the light goes are these instruments here that will be conducting all of the science that will be collected from Webb. You can see the other parts of the James Webb here, for example, the space bus, which is the other electronics and equipment that will be used to operate James Webb, star trackers so that it can be assured that it is locking in on what the scientists want it to lock in on and not just anything out there at all. So a very, very complex piece of machinery. I'd like to make some distinctions between the James Webb Space Telescope and some of the other great observatories, as they're called, that NASA has used and is in fact currently using. So here we have the electromagnetic spectrum. And just in this little section right here, you have what's called the visible spectrum. In that one small little section. To the left, you have UV rays and gamma rays. To the right of the visible spectrum, you got infrared, microwave, and radio waves. So down here at the bottom, here we see the Hubble Space Telescope. And the Hubble predominantly worked in what's called the visible part of the spectrum. Many of the pictures that you and I see that are released from NASA, there's a really good chance that those are coming from the Hubble Space Telescope. Hubble, though, did have a little bit of the UV and the infrared part of the spectrum covered as well. But again, Hubble was very focused on the visual, what we could actually see with our own eyes if our eyes were powerful enough to be able to see everything that there is in space. Over here on the right-hand side, we have the Spitzer Space Telescope. Now, the Spitzer Space Telescope was retired a year ago, in January of 2020. And as you can see, the Spitzer Space Telescope was focused in the infrared. Okay? Here we have James Webb, also focused in the infrared, but a much larger portion of the infrared than you see Spitzer was focused on. In addition, James Webb will have a very small portion that it will be able to accommodate the visual component or spectrum of the electromagnetic spectrum. So the NASA's great observatories, and others are not listed up here like the Chandra, are focused on different sections of the electromagnetic spectrum. So you may ask yourself, okay, so what's the big deal about infrared? So here is an example of what infrared technology can do for us. On the left-hand side over here, these are the pillars of creation. And this is a picture that the Hubble Space Telescope actually took. And you can see that there's a lot of dust. And I will point out, this is all the dust here that create the pillars of creation. What is space dust? Well, it's a collection of dust and gases that will and can potentially create things like stars. So what will infrared do for us? Infrared, and there are two types noted here, near infrared and mid infrared. You can see, like for example in this picture, we can see stars here that were hidden by the dust. Okay? So infrared penetrates this cloud of dust and allows scientists to see what's going on in it and through it. All right? So that will allow Webb to see things that Hubble could never see due to its limitations of looking at the visible part of the spectrum that I mentioned a moment ago. I want to show you how big Webb's primary mirror is. As I mentioned earlier, it's 18 hexagon-shaped mirrors that all collectively are run individually by motors in the back that you can't see, and they are all basically they all come together to form what we can think of as one large mirror. So on the left-hand side you have Hubble, and Hubble has only one primary mirror, and it's roughly between 7 to 8 feet across. Webb's primary mirror is about 21 feet across, so about 3 times the size of Hubble's. Now when it comes to imaging things out in space, bigger tends to be better. Why? Because the bigger your mirror, the more light you can collect. And when taking images, either infrared or visible images of anything, stars, nebulae, dust, gas, the bigger your mirror, the more light you can collect. And that's what astrophotography is all about. It's about collecting light, and the more light you can collect, because you have a large mirror and the amount of time that you use, the more time that you use to collect light, the better the quality of your image. Webb is going to have a lot of advantages over Hubble because of the size of its primary mirror. Okay, so again, all of these mirrors will work in conjunction with one another. They're all adjustable, and they'll all be adjusted so that they all focus to create one mirror, and the light that hits each of these mirrors will then go to the secondary mirror, which then will go into the tertiary mirror that I was mentioning a moment ago. All right, how will NASA talk to Webb? NASA has what's called the Deep Space Network. And the Deep Space Network is a collection of very large radio telescopes. Very large radio, let me show you a picture of them. This is a radio telescope. So it's a big dish. And there are 3 of them around the world. You have one which is in Goldstone, California, right near Pasadena. NASA has one in Madrid, Spain. Okay? And the third one is located in Canberra, Australia. And so you can see that they're equally positioned all around the globe, so that regardless of where the Earth is in its orbit, and regardless of where James Webb will be out in space, there will always be a line of communication between NASA and the Webb Space Telescope. As a side note, the Deep Space Network, often simply referred to as the DSM, is the way that NASA communicates with most of its satellites and rovers that are out in space. For example, the now famous Perseverance rover on Mars uses the Deep Space Network to communicate with NASA. Voyager 1 and Voyager 2 that were launched way back in the 1970s, 1977, that are now both in interstellar space, use the Deep Space Network to communicate with them. There are Mars orbiters and Earth orbiters. All of these different satellites and rovers and landers are using NASA's Deep Space Network. So if you get the opportunity, go on the web, do a Google search for NASA's Deep Space Network, and they have a really neat website that will show you which ones are currently up and running and what they're tracking. And so it's a really cool thing to check out. All right, so now I'd like to talk about the science of James Webb. What science will be conducted? All right, so here are some of the questions that will be addressed by Webb. What was the universe like after the Big Bang? How do galaxies change over time? How do black holes form and grow? One of the questions that scientists hope to address when it comes to black holes is the question of, do black holes create galaxies, or do galaxies create black holes? How do stars form, live and die? Webb will see back to the very first galaxies using the infrared technology that I was speaking of earlier. Hubble does not have the capability of going that far back in time. In other words, seeing that far back in time. What does that mean? Well, light travels at roughly 186,000 miles in 1 second. That means, for example, that if you were to walk out tomorrow and take a look at the sun, please don't look directly at the sun. You will severely damage your eyes. But if you look around and you see the light that has come from the sun and that's lighting up the area that you're in, please consider that it took 8 minutes for the light to travel from the sun to the earth where you are. That means that if for some reason, and of course this is not going to happen, the sun shut off suddenly, it would actually take us 8 minutes to find out that that happened. Okay? Because that light already left and it's traveling through space, and it takes 8 minutes to travel that 93 million miles from the sun to the earth. All right? So Hubble was limited in that it couldn't see back to near when the Big Bang occurred, which was, what are the scientists are saying, over 14 billion years ago. But Webb has such an incredible set of mirrors that I mentioned earlier that they are hoping that they will indeed be able to see back to very close to when the Big Bang actually occurred. Another very exciting things that Webb will be taking a look at are what's called exoplanets. And an exoplanet is simply a planet that is orbiting a different star somewhere out in our Milky Way galaxy. It wasn't until the mid-1990s that we even knew that there were such things as exoplanets. So when the James Webb Space Telescope was being designed, that was not one of the objectives to study them, because we didn't even know for sure if exoplanets existed. Regardless, because of the great mirrors that Webb will have, it will be able to look for and understand the atmospheres of exoplanets. Okay, so we currently up to date know of over 3,000 exoplanets that exist. That's a far cry from the 2 that were discovered back in the 1990s. So we should be looking for a lot more exoplanets to be discovered in the relatively near future. All right. So with that said, my best resource to you is nasa.gov. And I would like to quickly show you the NASA website. If you've never been to the NASA site, resources on NASA's website, I specifically would like to point out Webb on here. If you go to the Missions tab, there is an entire section all about James Webb. An overview, tons of videos and images and media resources. So that's a great starting place if you would like to learn more about the James Webb Space Telescope. NASA.gov. All right. If you are not a subscriber to my YouTube channel, I kindly ask for you to consider subscribing, and please subscribe. I would appreciate it. And so now we have a short period of time for any questions. If anyone has any questions, you can put them in the chat box and I will see if I can answer them. So let's see, I'm seeing a question. You stated there is so many things that can go wrong upon deployment. My question is, with all of the money on the line, what is the protocol for retrieving Webb if something does happen? So here's the protocol. Unfortunately, there is no protocol because there is no way to go and fix Webb. It's a tough situation because Webb has so much potential, but so many things do have to go right with the launch. Launches can be very violent. The James Webb Space Telescope has been tested extensively, has been shaked and rattled, and to see how it will stand up to the rigors of launch, and then simply traveling through space with the solar winds with the heat of the sun, the radiation. If the sun shield does not deploy properly, that can start to cause problems with the mirrors. Yes, it is tough, and there are a number of engineers and designers and scientists that have worked many years planning out Webb, and so I would hate to have to be one of them in about the next 5 to 6 weeks when Webb is launched, because in some cases their entire work life has been dedicated to this instrument, and for simply one thing to go wrong, that right there could end the entire mission. A lot of money has been spent on this, but the way that I like to look at it is great things require great innovation and dedication and work. Nothing comes easy. And so if we want to learn awesome things, get a lot of awesome science out of this, we had to build a whole new type of space telescope, nothing that we've ever seen before or used before. And that's what James Webb will do for us. So I guess what we have to do is keep our fingers crossed and make sure all those motors and unlocking devices all work, and they work on time, and everything opens and unfolds and everything turns on the way that it should, because it would truly be a great loss if something went wrong and we could not fix Webb. It would be terrible. It would be terrible. Given that the Hubble and Webb have very different science capabilities, once Hubble's mission comes to an end, what capabilities will be lost that cannot be replaced? Well, one of the things that I can think of is that, as I said earlier, Hubble is using basically visible light. And so the pictures that we get back from Webb will basically be infrared pictures and not visible pictures. So we're not going to have all of the beautiful pictures that Hubble has taken over the last 30 years. So that's going to be a loss. But I think the science that will come out of Webb will make up for that loss. Again, Webb will be doing things that Hubble simply can't do because of its limitations, its small mirrors, for example. So yeah, we're gonna lose some of those awesome new pictures that could come from Webb if it was based in the visible light. But I think NASA made the right decision. We want to get the science out of this, and we don't necessarily want to focus on beautiful pictures. That's not to say that we're not going to see some incredible pictures coming from Webb, because we most certainly will. It's just going to be a little different than what we've been familiar with. So it's going to be horrible to lose Hubble. Hubble's been such an incredible observatory over the last 30 years. But eventually, like all things, Hubble will eventually come to the end of its life. And it's nice that NASA has a replacement. And so we're going to see what Webb will do for us. All right. So I hope that I answered those questions. And so I'll give you just another moment. If anyone else has any other questions, I'd be glad to answer them. If not, I assume, here's one more, I assume that the original design freeze for the components occurred, 20 years ago. Was there an opportunity to redesign or to incorporate more modern components, electronics? Okay, so I think what you're asking here is, since this was designed starting back in the mid-1990s, and here it is the year 2021, and it's finally being launched next month on December the 18th, was it upgraded as it went along? Yes, it actually was. In 2007, there were some pretty major changes made in the technology that Webb would be using. it has been significantly delayed. As I mentioned earlier, the original launch date was 2007, but there were a lot of engineering challenges, design challenges to get Webb to be what scientists wanted and needed it to be. And so as time passed, NASA decided, especially in the year 2007, we're going to upgrade our technology and do things that we couldn't have done in 1995 because the technology was not available. So yes, in fact, Webb was updated, and that's a great thing. So again, I hope that I answered your question. All right, so we are just a few minutes from the top of the hour. So I want to thank you so much for joining me tonight. As I said earlier, if you're interested in talks about NASA, I have a number of talks that I've archived here on my YouTube channel, so feel free to go back later on and check them out if you'd like to. But I do appreciate you coming tonight, and I hope that you have a wonderful evening. So I see one more question here. So let me see if I can maybe answer that one more question. Let me get rid of this here, or put myself in the middle. I was reading that it will take almost 6 months after launch to get real science data. Can you account for this delay? Yes, I can account for the delay. It's going to take roughly about a month to get it from Earth to the Lagrange point 2, and then it is in fact going to take 6 more months before the science starts. And here's the primary reason. They have to cool down the telescope. And it's going to take roughly about 6 months for the temperature of the telescope to come down to where it needs to be before they can fully operate the James Webb Space Telescope. Okay, so it's really based on temperature, and temperature is vitally important to the operation of JWST. So interesting, yes. So we're not going to be getting science back within just a couple weeks of it arriving to L2. It's going to take, and that's good that you pointed that out, it is going to take about 6 months. So we're looking at probably May, June of 2022 until we start to see some real science coming out of James Webb. But when we start to see this science coming out, it should be some really incredible, awesome science if all goes well. So please stay tuned and go to that nasa.gov website, and they're going to be reporting all of the awesome information that's going to be coming from this incredible NASA Great Observatory. All right, so I see some of you thanking me, and I really appreciate you coming. This is my pleasure. I love talking about NASA and space exploration, so I appreciate you coming tonight, and I wish you the very best. Happy Thanksgiving, and take care of yourself. So good night.